Dear students, in this lecture we are going to see principal sources of optimization in the 5th unit code optimization in compiler design. We all know that there are 6 phases of compiler. Number 1 lexical analysis, number 2 syntax analysis, third phase is semantic analysis, fourth one intermediate code generation, and the 5th phase is code optimization, and the last phase is code generation. So before generating the target code, there is a need for code optimization. So why we need code optimization means it will reduce the lines of code. That means the number of statements will be reduced if there is a optimization. Then it will reduce the running time of the program. So obviously the performance and the speed will be increased, and we can take the advantage of some machine idioms. Machine idioms means machine instructions. We can make use of the instructions efficiently. So these are the advantage of using optimization. So we must optimize the code. Once the intermediate code is generated, we have to optimize the code, then only we have to generate the target code. So in this optimization, we have some basic sources, basic techniques for optimization, that is majorly broadly divided into 2 types. Number 1 is function preserving transformations. Number 2 is loop optimization. Under function preserving transformation, we have 4 techniques. Number 1, common sub-expression elimination. Number 2, copy propagation. Third one is dead code elimination. And the last one is constant folding technique. Under loop optimization, we have 3 techniques. Number 1, code motion. Number 2, induction variable elimination. And the third one is reduction in strength. So totally we have 7 basic techniques in loop code optimization. We are going to see one by one with example. Let us start with the first one, common sub-expression elimination. It can be called as CSE. In 2 marks, it can be asked as define the term CSE. It means the common sub-expression elimination. As the name itself implies, we have to eliminate the sub-expression which are present common for 2 or 3 statements. Let us see one example. A equal to x plus y minus z. That is one statement. B equal to x plus y minus g. C equal to x plus y minus k. So these are the 3 statements that are scanned by the compiler. So here the expression x plus y is common in all the 3 statements. No need to use all these statements again and again. So we can optimize like this. Let us take one more variable t. Then we can substitute this x plus y. T equal to x plus y. So this x plus y is a common expression. We can substitute, we can assign it to t. So after optimization, these statements will become a equal to t minus z. B equal to x plus y can be replaced with t minus g. C equal to t minus k. So this is the first optimization technique called common sub-expression elimination. So these are the statements before optimization. These statements we are getting after optimization. Yes. So shall we move on to the second one? The second technique is the copy propagation method. Under copy propagation, here itself the name implies, for example, f equal to g. You are having some assignment statement. Instead of f, we can replace the statement as g. This is the common, this is the syntax. So we can make use of g wherever f is used. For example, let us take one statement, x equal to t1. Then a of t2 equal to y. Let us assume some statements. A of t10 equal to x. Go to b2. I am using unconditional looping statement go to. Go to b2 means it will go to some label b2. Just we are taking for an example. So this is before optimization. After optimization, by applying the copy propagation method, instead of using x again here, we can make use of t1 here. So this will become x equal to t1 because I have copied this x to t1. So no need to use x again. A of t2 equal to y. A of t10 equal to t1. Don't put x here. Then go to b2. So this is the technique behind copy propagation. Before optimization, the statements will look like this. After optimization, I am replacing this x with t1. No need to use the x again. So that is the second technique. Now we move on to third one, dead code elimination. There are two kinds of code, live code and dead code. Any code which is currently used by the program, that is called as live code. Any code which is not at all used in the program. In a particular program, we can have some statement, but that statement cannot be used anywhere in the program. That code is called as dead code. So we have to eliminate the dead code because there is no use of placing the particular statement. It is a wastage of memory only. So once if the memory is allocated, obviously the execution time will get increased, so the speed will get decreased. But the ultimate thing is we have to reduce the running time of the program. That is the technique behind optimization. So in case if we find any dead code, means we have to eliminate the dead code. Let us see one example for this dead code elimination. A equal to 3, B equal to C plus D. We can assume any example. X equal to Y plus Z. Something I have written. Okay, so here I have assigned A equal to 3. The next statement is B equal to C plus D. Assume that C, D, Y, Z, X are declared already. So I am going to add these two statements and I am going to assign it in B. Here I am adding Y and Z and I am assigning it in X. Here in both these statements I have not used A at all. But I have declared the variable, initialize the variable A equal to 3. There is no use, there is no purpose in using this statement. So we can eliminate this code. So after optimization, the code will be B equal to C plus D, X equal to Y plus Z. That's all. So this A equal to 3, this is called as the dead code. We have to eliminate the dead code to improve the performance or the efficiency. So far we have covered 3 techniques under the function preserving transformation. The last one is the constant folding method. It means I am going to replace some expression with a constant. That means the name itself, I am going to fold the expression, a lengthy expression, into a simple constant. That is called as constant folding method. In all the programming languages, users can cross this kind of statement. X equal to 1 plus 3, Y equal to A minus 9, Z equal to B plus 10. So let us take this example. Here X equal to 1 plus 3. While the compiler is compiling the statement, 1 will be assigned somewhere, plus will be assigned, 3 will be allocated some memory. So this will take some time to execute this expression, then only the result will be assigned to X. But no need to use this statement because X equal to 1 plus 3, it can be replaced as what? X equal to 4. I can do the addition operation previously and I can substitute the constant. So this is the expression. This expression is replaced with a particular constant. That method is called as constant folding method. But these two statements I can't change. We can't change. Y equal to A minus 9. A can be any variable. You have to subtract from 9 later. Then Z equal to B plus 10. Suppose, assume that instead of B, I have 5. In my statement itself means this is also in this statement also we can apply the optimization technique. So instead of using Z equal to 5 plus 10, what can I do? Z equal to 15. I can add and I can replace it with a particular constant. This method is called as constant folding method. Yes, so far we have seen 4 techniques under the function preserving transformation. Now we are going to see the loop optimization method. Under loop optimization, we are going to see how the optimization technique is used in for loop, while loop, do while loop, etc. So that is the main category. Under that, the first one is code motion. I am going to move the code outside the loop if it is not at all needed inside the loop. Let us take one example. While I less than or equal to t plus 3, x equal to x plus I. etc. Some statements I am having. So how the compiler will go through? It will enter into the while loop, it will check the condition while I less than or equal to, then there is one expression. It will first compute this expression, then assign a result, then it will be checked with the I variable, whether I is less than or equal to that particular value or not. Then only it will enter into the while loop. So obviously it will take more time. Instead of using this expression inside the loop, I am going to move this code outside the while loop. So what can we do? We can assign this expression to another variable. Y equal to t plus 3. I am going to just assume any variable. I am using y. Y equal to t plus 3. So inside the for loop, what can I do? While loop. While I less than or equal to y. No need to use the expression. I can move the expression outside the loop. That is called as code motion. Moving the code outside the loop. This is the particular code. So I am assigning it to a particular variable. Then I am substituting here. So while I less than or equal to y, x equal to x plus I. Yes, so this is the technique behind code motion. These are the statements before optimization. These are the statements after optimization. Like this, I can use for loop, do while loop or any looping statements. The second one is the induction variable elimination. I have to eliminate induction variable which is used more than once in a for loop. The best example is for I equal to 0, j equal to 0, k equal to 0. Like that I can have different initialization. I can have multiple increment, decrement also. Normally we won't cross this kind of statement, but this is also used in some complex statement. The compiler will face an issue if it look at all these statements. So for that only we are going to do optimization here. That is called as induction variable. So these are the induction variables. If the variable is no more needed inside the for loop, provided the meaning should not get affected, then that variable is called as induction variable. I can replace that variable with some other variable. So here in for loop, for I equal to 0, multiple declaration, j equal to 0, k equal to 0, I less than n. Some condition I have given I plus plus, j plus plus and k plus plus. Either you can use increment or decrement operator. In this case, no need to use all these variables. I can replace just with one variable. For I equal to 0, I less than n, I plus plus. No need to use this j and k. I can simply replace it with I. T equal to a of I. L equal to, I can have it as b. B of I. Yes, so this is the optimized code. This is the code before optimization. I have eliminated the variables j and k. There is no need for increment of j and k of variable. So that is the induction variable elimination. The last technique in loop optimization is reduction in strength. It is little bit controversy to the priority. Normally we have preference for all the operators. Star and slash are having higher preference than plus and minus. So this is the precedence of operators we have discussed in the previous classes. But generally strength means plus is having lesser strength than multiplication. Then minus is having lesser strength than division. So these are the important things you have to remember. Instead of using multiplication, I can replace it with addition. Similarly, instead of using division, sometimes I can replace it with subtraction. That is called as reduction in strength. Why we are going to reduce the strength means it is one of the optimization methods. I can make use of the machine idioms. I can take the advantage of machine idioms. That is the reduction in strength. Let us take simple example. A equal to I star 3. So what is the meaning? I am going to multiply 3 times. with I and I am going to assign it with A. So star is having, multiplication is having higher strength. I am going to replace it with addition. Instead of using I star 3, what can we do? Here I am going to multiply 3 times I. Instead, I can have it as I plus I. Is the meaning changed? Not at all. So, instead of using the multiplication, I have replaced it with addition operation, that is called as reduction in strength. We can make use for division operation also. It is rarely used in some complex statements. Yes. So, these are the 3 optimization techniques under loop optimization. So as a whole, let us revise all these things. Totally there are 7 techniques under optimization, broadly classified into 2 types, function preserving and loop optimization. Under function preserving we have 4 types, under loop optimization we have 3 types. You have to write each technique with example. As we have discussed now, before optimization what is the code, after optimization what is the code. Likewise you have to explain with example for each technique. So these are the principal sources of optimization. I hope you are clear with this topic. Thank you, students.